All right. So we'll first define what they are, and then we're going to do, of course, we'll do a ton of examples. So let me define what they are first. So an Euler path, so the first thing is an Euler path. This is pronounced Euler, like someone who harvests oil, even though it's spelled weird. An Euler path is a path that travels through every edge of a graph once and only once. Okay. So as we also know, each edge must be traveled and no edge can be retraced. So that's just true of a path, just reiterating that. Okay, so that's an Euler path. So we'll first introduce that. It's a path that travels through every edge. So it's basically a path that hits every edge. Okay, let's talk about an Euler circuit now. An Euler circuit is just an Euler path that begins and ends at the same vertex. So basically you start at a vertex and you got to get back to that vertex, and you have to hit every single edge in the whole graph, and you can't hit an edge more than once. Okay, so that's an Euler path and Euler circuit. Those two things are going to be the study of our class today. Oh, Bryson just wanted to admit, I'll let him in. Okay, so that's an Euler path and an Euler circuit. And so we're going to practice some of these. So let's just take a simple example here. Okay, I'll take a nice little, draw a little house here. Okay, so that's my little house. That's my graph. Okay, and let's say I wanted to create an Euler path. So an Euler path, I could start here. I'm going to do this in a different color. Give me a second. So an Euler path could go like that. Okay. Then it could go like this. Then it could go like that, for example. Then it could go up. Then it could go up this way. And then down that way. And then it could go down this way. And then it could go across that way. Notice I hit every edge only once, and I hit every edge. Okay, that makes it an Euler path. Okay, so very, very simple example. All right, so now let's talk about Euler's theorem. So Euler's theorem says a couple things. If we have a connected graph, you guys remember what connected means? Connected means that I can get from any vertex to any other vertex with a path. So there's no break in the graph. So just reviewing here, I'll erase this in a minute. So a connected graph. So like, for example, this would be a disconnected graph. because I, for example, can't get from this vertex to that vertex with a path because there's a break right here. So as long as the graph is connected, we can use this theorem we're about to use right now. So Euler's theorem says, 1, if the graph has exactly 2 odd vertices. Do you guys remember what odd degree means? The degree of a vertex is just how many edges come out of that vertex or come into it. So if the graph has exactly 2 odd vertices, then it has at least one Euler path. Okay? But no Euler circuit. So it means there's not possible to ever start and end at the same point. So if it has exactly 2 odd vertices, and note that each Euler path must start at one of the odd vertices and end at the other one. Okay? So we'll do some examples of that in a minute, but if it has 2 odd vertices, exactly 2 odd vertices, we know it's going to have an Euler path. It's going to have no Euler circuit, and the way we'd find the Euler path is we'd start at one of the odd vertices and we try to end at the other one. That's how we would think about it. The example we just did, I can point out, we found an Euler path in that. If you remember here, it looked like this. Okay, and if I look at all these different vertices here, those are my vertices. It looks like it has 2, this is an odd vertex right here, right? Because there's 3 vertex edges that come into it. This is an odd vertex as well. All the rest of them are actually even. This one right here is even. 1, 2, 3, 4. This one's even. It only has 2 coming into it. This one has 4 coming into it. So this one has exactly 2 odd vertices. And if you remember, I actually started at this vertex and ended at that vertex. So the one I just did is an actual example of Euler's theorem part 1. So if it has 2 odd vertices, then it has exactly, it has an Euler, at least one Euler path. Could have more than one way to get there. It could have more than one way to get from this starting point to that ending point, but it's going to have at least one way. Okay, so part 2 of Euler's theorem, and we're going to practice all this, so don't worry about remembering it all. If the graph has no odd vertices, so we're going to say it another way, has all even vertices, it has at least one Euler circuit. Okay? And the Euler circuit can actually start and end at any vertex. Okay, in that case. So that's part 2. Part 3, if a graph has more than two odd vertices. Then it has no Euler paths or circuits. Okay, so those are three big things that help us to identify how this stuff's going to work. Okay, so let's try to narrow this down a bit. Okay, so big idea, two odd vertices. That means we have an Euler path, no circuit. All right, all even. We got an Euler circuit. No Euler circuit. And then greater than two odd, no Euler path, and no Euler circuit. Both. Those are the three cases. This is part one of Euler, part two of Euler, part three of Euler. Okay. Okay, so let's do an example here. I will draw a picture. There we go. Like this. Let's get a graph going. Put my little dots. These are my vertices, the dots. Okay. There's my vertices. I'm just labeling them here for a second. Okay, so there they are. Let's examine, which in the theorem, which case we have here. So let's take a look here. Looks like A and B. Let's just list these here. If we got A, B, C, D, E, F, G, H, I, and J. We're going to list these, and we're going to make a little column. We're going to determine if they're odd or even. So A looks like it's even because it has two edges coming into it. So A is even. B is even, two coming into it. C looks like it's even, 1, 2, 3, 4, right? So C is even. Looks like D is also even. E and F both have two coming into them, so they're both even. G is even. It has 4 coming into it, so is H. Those are both even. I has 2 and J has 2. So these are all even. All the vertices have even degree. Okay, so that tells me that out in the theorem that we just did, if I go back and bring that up, if they're all even, we have an Euler circuit. Okay, so there's an Euler circuit, so that means we could probably find one. So let's see if we can find one. Well, there's probably lots of different ones. Remember, it said in the theorem that I could start at any one and then when I have all evens. So I'm going to start at H. Why not? I'm going to start right here at H. So I'm going to go from H over to G. Then I'll shoot over to E. Then I'll shoot up to C. And the rule of an Euler circuit is I got to get back to H, but I can only trace everything once. And I have to hit every single one. So I'll go down here now to here. Then I'm going to shoot down to here. Then I'm going to shoot over to here. and then I'll shoot up to H, and then I'll shoot up to D. Whoops. Yeah, that's fine. And then I'm going to shoot over to here, up to there, up down to there, over to there, and back to H where I started. So that was an Euler circuit. And my letters in order were H, then I went to G, then I went to E, then I went to C, then I went to G, then I went to I, then to J, then to H, then to D, then, whoops, then I went to C, then I went to A, then I went to B, then I went to D, then I went to F, then I went to H. So I started and ended with H. Now notice, I hit several vertexes more than once. That's actually okay. So take a look here, for example, I hit H a lot of different times here. I hit it 1, 2, 3 times. Okay, I hit C several times too. C, C. Okay, I hit a couple other things a couple more times. So you can hit, when you're doing an Euler circuit or an Euler path, you can hit the vertices more than once. You just can't hit the edges more than once. You have to hit each edge just once. Any questions on that, guys, or does that make sense so far? What an Euler path and an Euler circuit are? You could all just pipe in and say yes in the comments if you're okay. So let's do some more then. Let's do some more. I'm going to give you one here and see what you think. So if I do, I'll draw a picture here. All right, so use Euler's theorem and try to tell me, does that have an Euler circuit, an Euler path, or neither? Does it have an Euler circuit, an Euler path, or neither? So the way you want to look at that is look at the degrees of each vertex and then try to use the theorem to determine it. So I'll write those out here. A, B, C, D, and E. Find your degrees and then see if you can use the theorem. Once you have it drawn, I'll go ahead and you can write your answer in the comments if you think it has neither, has an Euler circuit, or if it has an Euler path. A little bit of practice here. Anyone else get what they think it is? So Haley says neither. So let's go through it here. So what's the degree of A? Well, let's take a look. A looks like it has 3 going into it, right? So it's odd. Odd. B looks like 3 as well. So that's odd. C looks like it's even with 4 coming into it. That one's even. E looks like it's odd. And D looks like it's odd. Okay, so I have 4 odds. What does 4 odd vertices mean? Well, if you go back to our theorem, if I have greater than 2 odds, I have no Euler path and no Euler circuit. So it should be neither. Okay, this implies neither. Okay, everybody seeing how this kind of works? Okay, let's do an example here. It's a little bit harder. See if you guys can get this one. So in this one, you've got to first turn this picture. It's one of those room problems with the doors. Remember those? So you give some doors in here. You give your room so a house with some doors. Just kind of creating the drawing here. All right. So the outside we're going to call E. This is room A. This is room B. This is room C. This is room D. So you're going to look at each room as a vertex, and you're going to look at the doorways as your edges. So if I can get from one room to another, I'd create an edge. Like there'll be an edge between A and B, for example, and there'll be an edge between A and E. There's actually 2 edges that go to A and E, those 2 both. Because anytime that you go outside the house, you have to connect to E. And if there's 2 doors that go out from A to E, then we have to do 2 different connections. So first of all, create this graph, and then tell me if it has an Euler circuit or an Euler path or neither. So what this basically says is, can I walk through every door once if it had an Euler path? That would mean I'd be able to walk through every door exactly once and have a path through it. So try to create a graph first and then count your vertices and try to use the theorem. So take a few minutes to do that, then we'll do it. All right, let's take a look at it. Let's try to draw this out. So I'm going to actually raise this up a little bit. Give me a minute here just to make it more visible because I'm hitting the bottom of the screen, I noticed. So if I go A, B, C, D, and I'm going to put E over here. It doesn't matter. There's a lot of different ways you can draw this graph. I'm going to put E over there. So looks like A is connected to all 4 of them, right? You can go outside. Well, actually, it's not connected to D. So A is connected to E twice. So I'm going to do 2 connections to E, one there. And then I have to do a second connection to E, which is right there. I'm going to do that. Looks like A is also connected to, I'm going to fix this a bit here. Looks like A is also connected to B, and A is connected to C. Okay, so I've got A's connections done. Looks like B is connected to E. Looks like B is connected to A and D as well, which I already have the A connection done. I've got to add the D connection. Look at C. Looks like C is connected to E twice. Okay. Looks like C is connected to A, which I have. C is connected to D, which I have. Do not have, rather. And that's it. And then D looks like it's connected to B, which I have. C, which I have. And E. Okay. So now if I just look at those vertices, A, B, C, D, and E, looks like A is got 1, 2, 3, 4, so A's even. B looks like it has 3, so that's odd. C looks like it's got 1, 2, 3, 4, so that's even coming out of it. D looks like odd. It's got 3. 1, 2, 3. And E is 1, 2, 3, 4, 5, 6. So E looks like it's even. Okay, so it looks like I have 2 odds. All right, so if I have 2 odds, going back to my thing, 2 odds, exactly 2 odds, means I have an Euler path and no Euler circuit. Okay, getting back to my drawing, this means you guys were right. I have an Euler path. Now, if I wanted to actually find the Euler path, it's not super hard to do it. I have to start at one of the 2 odd vertices and end at the other one. That means I've got to start at, say, D, okay, and end at the other one. So let's see if we can figure out how to do it. So I go here, then I'm going to go, say, here, then I'll go here, then maybe I'll go here, then maybe I'll go there, then maybe there, then maybe there, then maybe there, around here, and end at B. And I hit every edge once. That's a way to do it. There's more than one way to get that Euler path in this picture, but the way I did it was one of the ways. Okay. And then the way you'd actually list that, if you really wanted to list it, is you'd list the letters in order of the vertices you started with. Okay. Now, if you could also do this by just drawing a path right through the, you can actually, if you wanted to, you could just figure out a way to draw a path. I could start at that vertice D that I just did and try to actually draw a path through all these. I could do something like this. Make sure I hit every door, right? Do something like that. And I hit every door, and I only went through every door once. And remember, I can hit the letters, the rooms, more than once, because those are the vertices. So that would be another way to look at it without having to draw the whole graph, is I just have to go through every door exactly once because the doors represent edges. All right, so now we're going to talk about how would you actually, if you have a really, really complicated graph, sometimes it's actually hard to find an Euler path or an Euler circuit because it's really complicated and you're going to be doing a lot of trial and error to try to find it. So we're gonna look at an algorithm called Fleury's algorithm, which helps you to actually find it without thinking. Remember we did that problem the other day in class if you were here. Remember the bullseye problem I gave you? Try to draw that without lifting your pencil and hit every, edge once, and basically what you were finding was an Euler path, although I hadn't introduced it yet. And we're going to look at an algorithm on how you can actually find it without having to do trial and error. It's called Fleury's algorithm. Whoops. Today. Okay. And Fleury's algorithm, you have an Euler path or an Euler circuit. So if you've used Euler's theorem and you have either an Euler path or an Euler circuit. So one if you have two odd vertices, okay, if you're in the case with two odd vertices, which means you have an Euler path, okay, choose one. Whoops. So the first thing you do is choose an odd vertice, okay, as to start. Okay. After you trace an edge, so choose an odd vertex, right? Whoops. After you trace an edge, kind of erase it in your mind. So the way I do it is I actually do a squiggly line to show I've already used it. And then if you're faced with a choice, when faced with a choice of edges to trace, okay, so if you, let's say you get to a vertex and you've got a couple different choices now where you can go next. When faced with a choice of edges, don't choose a bridge. You guys remember what a bridge is? So when you're faced with a choice, don't ever choose a bridge. A bridge is what do you call it? It's an edge that, if taken out, makes the graph disconnected. So we don't ever want to choose a bridge. Okay, so let's look at an example of this. A simple example. I will draw it right now. Okay, so if we take a look at this, A, B, C, D, E, F. Okay, so take a look at that picture. So let's look at each individual vertex first and show that this has an Euler path. Okay, so A is odd. Okay, so I'm going to write a little odd next to that. It's an odd vertex. B looks like it's odd. E looks like it's even, has 2 coming out of it. D looks like it has 4 coming out of it, so it's even. F looks like it's got 2 coming out of it, so it's even. And C looks like it's got 2 coming out of it, so it's even. Okay, so this has 2 odd vertices, which means it has an Euler path and no Euler circuit. Well, I know I've got to start at an odd vertice, so I'm going to choose to start at B. Okay, so let's start at B. And I've got to end at A because you got to end at the other odd vertex. So if I take a look, I've got a choice now, right? I could choose this, this, or this, correct? I have 3 choices. Well, the only rule is I don't want to choose a bridge. Well, if you take a look, guys, isn't this a bridge right here? And the reason it's a bridge is because if I delete it, it makes the graph disconnected because now A is off on its own. So I can't choose that one. So let's choose one of the other 2. Doesn't matter which. Neither of the other 2 are a bridge. Because if I eliminate that one, I can still get to E another way. If I eliminate that one, I can still get to D another way. So those are not bridges, so I can choose either one of those. So let's choose, doesn't matter which one. Choose that one, as long as I'm not choosing a bridge. Now I only have one choice, which is to go here. Now I can choose again. None of those are bridges that go out of D. If I eliminate any of them individually, I still don't disconnect the graph. I can still get everywhere I need to. So I'm just going to choose any one of the three. It doesn't matter. So I'll choose this one. Now I only have one choice, which is here. Now I only have one choice, which is here. Now I only have one choice that I haven't already used, which is here. And then, of course, my only choice left is here. Okay, so that route I just took was B, followed by E, followed by D, followed by C, followed by F, back to D, up to B, and over to A. And I hit every edge once and exactly once. And I used Fleury's algorithm. Choose an odd vertice to start. After you trace an edge, erase it in your mind. And the way I do it is I just do a squiggle of a different color, but you could do squiggle with the black, same color as well. And when faced with a choice of edges, don't ever choose a bridge. You can choose any other thing you want, and you'll eventually get a path, an Euler path. Okay. Okay, so now what happens? So that's if it's an Euler path, if you have two odd vertices. Whoops. Okay, let's say you have an Euler circuit. So let me see how I delineated that in a minute here. 2, okay. So 2 is if you have an Euler circuit, which is all evens, all even vertices, okay? Same procedure, but the difference is choose any vertex. As a start. So you can choose any one and use the same rule. Never retrace. So basically, once you've used one, you kind of cross it out in your brain. You can't use it again. And C, when faced with a choice, don't. Never take a bridge. Now, if you don't have a choice, you can take the bridge. Because sometimes you don't have a choice. The only choice you have is a bridge. This is only when faced with a choice you don't take a bridge. Like if you have two options, you don't choose the bridge. Okay. So let's take an example. So I'm going to draw this sucker. It's going to take me a second. And then I get a little triangle out to here. Draw a little square off of that. And then a triangle up here. Okay, so this is A, B, C, D, E, F, G, H. Okay, so let's take a look at that one. So if I kind of go through my A, B, well, let's just do them right on there. It's fine. It's really quick to verify they're all even. Take a look at A. A is even. It's got 2. B is even. It's got 2. C is even. It's got 4 going around it. D is even. It's got 4. E has got 2. F has 4. G has 2 and H has 2. So they're all even. They're all even. So that means that we're going to have an Euler circuit. So if I follow Fleury's algorithm, I'm just going to pick a random place to start. I'm going to start at F because I want to. Doesn't matter. I can start anywhere. And none of these are a bridge. If I take a look, I can pull out any of these. Not a bridge. I can still get to G down there by a different route. That's not a bridge. That's not a bridge because I can still get anywhere I want. That doesn't disconnect the graph. So none of them are bridges. So I can go anywhere I want. So I'm going to pick this one. Whoops. I just accidentally erased a bunch. So I got to change here. Okay. So I'm going to go this way. And then, of course, D, none of those are bridges again. So I can pick anyone I want. I'm going to go that way. It doesn't matter. So let's keep a track of this. So I went from F to D. Now I'm going to H. Now I only have one choice right there. So G. Now I only have one choice there. I'm back to F. That's fine. Now I got a choice. So I'm going to go over to E. Doesn't matter which way I go again. E. I only got one choice now up to B. I got one choice now over to C. I've got multiple choices. I'm trying to end at F, right? And so I'm going to go up here. Ding, 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 ding. A. Go down to D. It's kind of a long route over to C. And down to F. That's a big Euler circuit. Okay. So that is an example of where they're all even. And I can actually navigate around that. Okay. I'm going to have you try one here. Let me draw it. Okay. This has got a triangle here. So bam. Bam. There we go. And then it's got a loop. And then it shoots down to E over here. And that shoots over to E. And then it shoots down to D over there. There's a loop. And this one goes all the way around to there. Okay, so that's my drawing. So this is A, this is B, this is C, this is D, this is E. Okay, I'm going to tell you right now, if you check them all, there's two odd vertices. They are A, I'm just going to give this away right now, and D has 1, 2, 3, that's a loop. So A and D, so you're going to want to start at A and end at D and follow Fleury's algorithm, or start at D and end at A. All the rest of them, if you take a quick look, 1, 2, 3, 4, wait, that one is 5. So what did I screw up a connection here? Hang on a minute. So that one, oh, my bad. Yes, I did. Get rid of that. So now it looks like it has two odd vertices, which would be A and C, right? So you should be able to do an Euler path on that. So try that with Fleury's algorithm. Take a minute to try that. Okay, let's try this. I know you guys are still working on it, but what you want to do is to follow the algorithm. We got the two odd vertices, which are this one, which is a 3, and the C, which has 5 coming out of it. 1, 2, 3, 4, 5. Okay, so those are my two odd vertices. So I got to start at one or the other. I'm going to start at A. Why not? Doesn't matter. And all I got to do is make sure I'm not choosing a bridge when I have a choice. Well, if I take a quick look here, that's not a bridge, the one I just erased, because I can still get to B or A other ways. That's not a bridge because it doesn't disconnect the graph. And that's not a bridge because it doesn't disconnect the graph. So it doesn't matter which one I choose. You choose whatever one you want. Now, what you have to think about is every time you put a red line over something, you have to imagine that that is no longer in the picture for a second. So it's almost like this is the new graph. Does that make sense? It's almost like that is the new graph. Once you put the red line, it's like you've erased that. All right. So now it looks like if I have going from B, it looks like I can choose any one of these three. None of them is a bridge right now. Now remember, you're imagining that the red squiggly line is gone now. So if I just quickly for a second, if I take that out, not a bridge. If I take this one out to E, not a bridge. Doesn't leave, I can still get everywhere in the picture. If I take this one out, not a bridge, because I can still get everywhere in the picture I want to. So pick any one I want. So let's pick the one on the outside, why not? So I squiggle around to there, okay? Now I've eliminated some stuff. My only choice now is to go up here, isn't it? It's the only choice I have right now. So I'm back at C. Okay, now I've got some different choices. Well, looks like none of the ones left are gonna be bridges, even though I'm imagining the red ones are gone now. If I eliminate, well, it looks like right now, if I eliminate that one, I don't have a bridge. It's not a bridge because I can still get to B another way. Doesn't isolate B or anything. I can eliminate that one. That's okay. I can eliminate that one. That's okay. None of these are bridges. So just pick whatever one I want. So I'll pick this one right here. Okay, so let's just cal out what we've done for a minute here. I started at A. Well, let's go below. My bad. I started at A. I went to B. Then I went around to D. Now I'm at C. Now I'm going to A. And then I only have one choice now that I haven't already hit, which is to go along here, go back to C. And then I'm just going to go around the triangle. I'll go over to E. I'll go up to B. And I'll end at C. I hit everything once. I started at the first odd vertex right there, and I ended at the other odd vertex right there. So that's my path. My Euler path. Okay, this is an Euler path. Because I started at one of the odds and I ended at the other odd. Okay, looks like Haley's might work, so let's see if it does. I can, just for fun, I can go ahead and erase my answer. Let's take a look. I'm going to kind of delete, see if I can delete my path. Whoops. Trying to just delete the red part. It's hard to do. But I'll get it done here in a second. I'll have to redraw some black line. That's okay. So you went, let's see if hers works. She went from A to C. It's fine. And then she went to A. Well, you can't actually go back to A. That's a problem. So you see yours, Haley, you have A, C, A. You already went from A to C. You can't go back to A because that you'd be retracing something you already did. So you can never retrace on a path, an edge you've already done. So that one doesn't work. But you could go A, C, and then B and follow your thing. Let's see if it works. If I skip that A, B, then you're going back to C now. You see what I'm saying? You can't go back to C. So you're retracing lines. So once you've gone over an edge, you can't retrace it. Does that make sense? I think there was another line. Oh, did I forget another line? Oh, let me take a look at the picture. You're right. My bad. I forgot when I was deleting all that. I forgot to do this. So maybe you're right. So let's try yours now. So if I go A to C, let's try that. So let's go A to C. Then let's go back to A. You're right. You're right. and then I go to B, and then I go down to C, and then you saying that I should go over to E, and then you're telling me to go to B, and then around to D, and then up to C. That works too. Yep, that works. So there might be more than one other path. There's not just one right answer. And in your homework, you'll be able to choose different options. Okay. Okay, let's try one. That's a little bit more tricky. How about this one, guys? If I go like this, boom, boom. Put some dots on here. Okay. This is A, B, C, D, E, F, and G. Okay, first determine, does this have an Euler circuit or an Euler path or neither? And then if it has an Euler circuit or an Euler path, go ahead and try to find the Euler circuit or Euler path for it. So you got to use Euler's theorem first, and then second, try to actually find it using Fleury's algorithm. Take a few minutes to try this. And somebody actually list your ABCs in order, and we'll try a couple of them. I'm going to give you about 5 minutes to do this one. Okay, this one should be a path. Reason is if you take a look, all of them are even except for C and D, which are odd. They each have 3. Okay, so this one and this one have 3. If you take a look at all the rest of them, E is even, F has got 2, G has 4, B has 2, A has 4. So all the rest of them are even. So that means if I start at one of the odd ones, okay, so I have to start at one of the 2 odd ones. Remember, if you look at Fleury's algorithm, I have to start at one of the odds. So someone sent me one privately. That one isn't going to work because it starts at one of the evens. So we have to start at an odd, otherwise it's not going to work. Well, it might, but it's not guaranteed to. So somebody had sent this one. I won't say who it is because they sent it to me privately. But if I go from A to B, that's what they had. Then to C, this may work. We'll see. Then to D, and we're stuck now. Well, actually, maybe not because we can get around the bottom. I didn't catch that. D, then I can go to E. They said to go to E next. Then to F. Then to G. Then to A. Then it looks like back to G. And then to D. Problem is we missed that one. So it was close. That one was close. Okay. So let me erase those. Okay. So what we want to do is we want to start at either C or D and then just follow the rules of Fleury's algorithm, guys. This should not be trial and error. You don't want to think about this. You just literally follow the rules. So I start at C or D, start at one of the odds, doesn't matter which one. Okay, so I'm going to start at C. And then all I got to do is pick something that's not a bridge. So I have 3 choices, this, or this. It turns out none of them are bridges. The way I know none of them are bridges is because if I erase them one by one, the graph is not disconnected, is it? Because I can still get anywhere using these 2 bottom ones. Whoops, I just erased a bunch of crap. I can still get anywhere using these bottom ones down here. Okay, so that is not a bridge. So I'm going to choose that one. I'm going to go ahead and go to D. It's fine. Now I've got two choices, but neither of them are bridges, so I'm going to choose this one. Okay. And then I'm going to choose this one here. That's my only choice. Then this is my only choice right now. Okay, now now in this situation, okay, you take a look, I have a couple choices. This is a key point in this algorithm. I have this choice, that choice, and this choice. All right. I don't want to go to D. Here's why I don't want to go to D, because remember, I'm imagining that the red squiggle lines are all disappeared. If I go to D right now, isn't D now a bridge? Right here, the 1 to D is a bridge, because if I eliminate that, I can never get back to D, can I? I've disconnected D from the graph. So I can't choose that one, because now that I've eliminated C, D, D, E, E, F, and F, G, the squiggly lines, D's all by itself. I'll never be able to get back to it. So I can't choose that option. So I got to choose one of the other two. It doesn't matter which, because neither of them are going to be bridges. Because if I eliminate that, I can still get to A another way, for example. If I eliminate that, I can still get to the other side another way. I'm just going to pick either one of them. So you just follow the algorithm. Okay, now I've got to, I don't want to, so now take a look. I have three choices. Here we go again. My three choices are here, here, and here, correct? Well, out of those three choices, I cannot pick this one, because then if I picked G, I can never get back, can I, to this other half? So basically right now, the segment AG is a bridge, because if I choose it, if I eliminate it, it disconnects all the lines I have left. Remember, when you're erasing these, okay, think of the red lines as erasing them. You have to think about whether it's going to be a bridge. So I can't choose that blue one. I'm going to do this another way in a second. That's, I think, going to help you guys. So I'll choose any of the other two. And then I only have one choice. And then I only have one choice that I haven't used. And then now I only have this choice. And then I end at D. So that's my path. That was a hard one, and here's why, because bridges emerged in the middle. So let's delete all these red lines, and I'm going to show you another way you can do this, okay? So another way you can do it is you can use a pencil, and you can actually erase lines as you go and record your path. So let's do this again. Let's start with C. So we're going to start with C. All right. We're going to first go over to D. So we're going to eliminate that one. So we're going to go to D. So we've eliminated that now. So just erase it whenever you use it. Now we'll go up to E. So we'll erase that edge. So as we go, we're going to erase every edge that we use. C, D, E. Now I'm going to go over to F. It's my only choice, right, for me. It's fine. So now I've used that. F. Now I'm going to go to G. That's my only choice. Okay, so I've used that. So now I've gone to G. Now, I can't go to D, because if I go to D, the segment now, it's a lot easier to see now, right? DG is a bridge in the new drawing, now that I've erased all the other ones. Right, DG is a bridge because it leaves D all by itself, so I can't choose that one. So I have to choose a different one. So I'm going to choose to go to A around from G on one of the two strands. So I'm going to eliminate that, which puts me to A. Whoops. Okay. Now, from A, I can go to either B, C, or G, but I don't want to go to G. The reason I don't want to go to G is because if I go to G, AG is a bridge right now, because it'll disconnect the parts of the graph that are left, correct? So I can't go there. So I'm going to go ahead and go to B next. Whoops. Then my only choice is to go to C. Whoops. And then my only choice from C is to go to A. And then my only choice from A now is to go over to G. And now I am eliminating a bridge, but if the only choice I have is a bridge, I take it. The only time I avoid the bridge is if I have another choice. So I eliminate that. So now I just went to G again, and then I go back to D. Bam. This is my Euler path. That's not the only way to do it. I could have started at D and done a similar thing. Okay. And Haley, I looked at yours. Yours does look right. So that also works. It's a little bit different, but it does work. So everybody's starting to get a hold of this. So it might be easier for some of you guys just to erase them as you go, because then it's a lot easier to see what things are bridges and what things are not once you have the leftover lines left. Okay, I can see it with the reds there, but sometimes it's easier to actually go ahead and erase it. Then it's clear to see what the leftover graph is and when you need to avoid a bridge. Again, if the only choice you have is a bridge, then you have to take it. But if you have 2 or 3 choices, always avoid the bridge and just pick any one of the other ones. It doesn't matter which you pick. It'll end up working out in the end. All right, let's try another one. I think practice is the key to this, right? Okay. So I'm going to draw one here. Where is it? There it is. All right, this is a fun one. It's kind of a mess. There's a lot of dots in this one. Let me go up here. Let me go there. Let me go down there. Let me go down there. Okay. And these are all vertices. Let's mark all these. The ones where they cross in the middle of the squares are actually not vertices, even though they do cross there. Okay, there's my basic picture. This is A, B, C, D, E, F, G, H, I, J, K, and L. Okay, so let's just examine this. It turns out that this is going to be all even vertices if you look at it. I'm just going to give that away. You could test it, obviously, but you can test each one individually, but I'm just going to tell you that. So you're going to actually find an Euler circuit for this. So see if you can find an Euler circuit using Fleury's algorithm, okay? So take a second to try that. I'm just telling you right now, they're all even. So you can start at any one. Doesn't matter where you start. This will work. And I want you to try the method of deleting or erasing it as you go so you can recognize when you're running into bridges during the process. So take a minute to do that. A few minutes. Okay, let's actually go through this one. So again, since it's an Euler circuit and they're all even, I can start anywhere I want, okay? So does anyone want to give me a place to start? Pick a letter, doesn't matter the letter. Okay, let's start at C, fair enough. So let's start at C. So let's write down C as our first point, okay? Our first one, C. So I can pick to go anywhere. None of those are bridges right now. So I'm going to erase any one I want. I'm going to erase the one to A. Okay, so that's A. Now I only have one choice, which is to go to D, right? Okay, so I'll go to D next. Now, D, none of those are bridges. The one to E, to C, to H, or to G, none of them are. So I'm just going to pick the one to G. Why not? Okay. Now I'm sitting at G. None of those are bridges. The one to C, K, H, because if I eliminate any of them, I don't create a disconnected graph. So I'm going to go ahead and eliminate the one to C. Again, I'm not thinking, I'm just following the algorithm. Just don't eliminate a bridge. That's all I got to think about right now. Now I'm going to go to D, because I can go to either H or D, and neither of them are bridges. So I'm going to eliminate the one to, whoops, I accidentally made that one line, and I shouldn't have done that. Okay. So eliminate the one to D. So I'm going to write that down. Now I'm going to go to E, because none of the rest of these are bridges. Okay. Sky, no. That's my dog Sky, by the way. I'm going to go to E. Okay, so write that down. Now I'm going to shoot up to B, because that's not a bridge. Eliminate that one. Now my only choice is F. So I went to B. Now I'm going to go to F right here. Eliminate that one. I can shoot down to J. That's not a bridge. It does disconnect the graph. So I'm going to go to J. Now I'm going to go over to I. That's not a bridge. So I'm going to go to I next. Oh, shoot. So hang on. Did that. So I went to I. My bad. Okay. Now I'm going to go over to down to L, because that's not a bridge. So I'm going to eliminate that. Trying to record these as I go. This is a long journey. Now my only choice is J. So I'll go there. Now that I'm at J, my only choice is E. Okay. I'm going to scroll here. Now I'm going to go over to F. That's not a bridge. And my only choice from F now is to go to I. And then from I can go to E if I want to. It's not a bridge. And then from E, I'm going to shoot over to H. That's my only choice right now. So I'm recording this as I go. Then from H, I'm going to shoot over to I. That's my only choice. I'm going to go up to D. And then D, my only choice now is to go to H. So I eliminate that. Now that I'm at H, I can go to C or G. This is a pivotal moment. I can either go C or G. Well, I don't want to go to C because that isolates C, right? Okay. Or something's wrong here. Did I accidentally erase two at once? Because I'm not able to. Oh, you know what? I did. My bad. Hang on a minute. C-A-D. I'm missing one line. My bad. When I erased, I just noticed in my path. Sorry, that should still be there, I believe. No? Is that right? So if I go, oh, shoot. Dagnabbit. Did anyone see where I may have accidentally erased two at once? I definitely did somewhere. Doggone it. Because now I can't get back to C, I don't think. Bam, 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 bam. I cannot. This is the problem with doing this erasing method. Shoot. So I'm going to have to redo this one. We're going to have to redo it. Sorry, guys. So let me erase this. That is an absolute bummer. This is the problem when I erase with my iPad pen. I think I must have erased a couple at once, unfortunately. So let me redraw this one. This is all right. This is our last problem of the day anyway. So let's just double check. These are all even. Okay, so A is even, that's 2, B is even, C is 4, D is 1, 2, 3, 4, 5, 6. E is also going to be 6. F is 4. J is 4. I and J are 6. H and I are 6, rather. G is 4. K and L are 2. Shoot. Dagnabbit. I must have accidentally erased one. So we're going to start at C again where recommended. So let's do this the right way now. Let's go carefully. All right, so we start at C. I'm going to go up to A. All right, so I'm at A. Then I'm going to go down to D. That's my only choice right now. And then I'll go over to E. Erase that one. Then I'll go up to B. It's not a bridge. And then I'll go down to F. That's my only choice. And then from F, I can go to either E, I, or J. I'm going to choose J. So I've got to erase the path down to J. Then from J, I'm going to go down to L. And then I'm going to go to I. It's my only choice now. Okay, now I'll shoot back over to J. Then my only choice is to go to E now. Then I'll shoot over to F. Now I'm going to shoot down to I. It's my only choice now. Now I'll shoot up to E. My only choice now from E is to go to H. And from H, I'll shoot over to I. That's not a bridge. Then I'm going to shoot up to D. It's my only choice from I now. Now D, I'll go to H, down to H. That's not a bridge. Then I'll shoot down to K. My only choice from K now is to G. Okay. Now I go to H. I can go to H if I want to. And then from H, I'll go to C. And then from C, I'll go to D. And then from D, I'll go to G. And then from G, I'll go back to C. And I've done it. So sorry about that first run, guys. That was a mess. But I think what happened is, like I said before, I just deleted a couple at once by accident with my eraser on my pen. So I must have missed it. So Now I've done the whole thing. I didn't delete any bridges if I had a choice, and I was able to get from C to C. So this is an Euler circuit right here. Okay. Bam, Euler circuit. So that pretty much concludes that section.